Okay. Good afternoon, all. Now, in last lecture, we have completed our second chapter. It is study of the ferrous materials and its alloys. In that we have studied different types of plain carbon steels and different types of the alloy steels. And after that, we have discussed about the cast irons along with its brief classification and brief applications. Now, this is the third chapter. This In this chapter we are going to study the non-ferrous metals and their alloys, and after that we are going to discuss the some composites and nanomaterials. These are some modern materials which are developed nowadays, that is composite materials and nanomaterials. In your syllabus, only introductory part of composites and nanomaterial is there, means what is the meaning of composite material or what is the meaning of nanomaterial, their classification, and their general applications. We are not going to discuss it in detail, but these are having means you can say that the composites and nanomaterials, all these are futuristic materials, means in the future we are going to deal with that only composites and nanomaterials. These are having wide scope and wide applications, but in your syllabus only introductory part is there, means what is the meaning of composite, what are the different types of the composites, then its general applications. And in the same way we are going to discuss related to nanomaterials also. And here non-ferrous alloys, that syllabus will be like this. You can go through that. Means this chapter will be divided in the three parts. First, in the first part we are going to deal with the non-ferrous alloys. In that we are going to discuss the copper and copper alloys. In that we are going to deal with different types of the brasses and different types of the bronzes. Then after discussing copper and copper alloys, then we are going to deal with the aluminum and its alloys. And one precipitation hardening step is there in the aluminum alloys. That is very important part as far as your final examination will be concerned. Compulsory one question will be there on this steps in the precipitation hardening. And then the next we are going to discuss some lead and tin alloys, and very few specific alloys we are going to discuss here. That is the babettes and nickel alloys we are going to discuss here. And after this non-ferrous alloys, we are going to deal with the composite materials and nanomaterials. In this we are going to deal with the their means what is the actual concept of that, what is the composite material or what is the nanomaterial, then their actual composition, their classification, depending on their what you can say that their phases or their material, how their properties are, and how we are going to decide their applications. uh, these two materials are very futuristic. As far as suppose you want to um, do your project for your final year, then you may look into this composite materials and nanomaterials also. Means you can develop a composite material and you can conduct different testings on that composite materials. It may be considered as your final year project. Okay, you can develop a you can take, first understand what is the meaning of composite material, then how to develop a new composite material. You can develop that in our lab, metallurgy lab. All facilities are available there, you can develop that, and you can do the study of that material related to its properties, like how much tensile strength we are getting, what will be its structure or microstructure, then what will be its hardness. All these tests you have to conduct. Means you have to first prepare that material, and you have to conduct or you have to check its properties, and you can make a report on it, and it can be considered as your final year project. Okay. If you are willing to do your project in this composite material, it will be having a wide scope, and these composite materials are widely used in nowadays. These are widely used in your aircraft industry. Okay, specific applications are there in different industries, we are using that. The nanomaterials are having wide applications in the medical field, or healthcare industries, or different industry in the chemical industries also. So you can look in this composite material and nanomaterial. such a way that you can do your final year project in these composite materials or nanomaterials. Okay, now we will start now. We will start with the non-ferrous alloy. Now here are some requisites. These are prerequisites, means some concepts you should know before starting this chapter. That is the engineering chemistry. Engineering chemistry means you should aware about what is the meaning of metal, what is the meaning of non-metal, like this, and you should have gone through some workshop practices, and you should have knowledge regarding some basic manufacturing processes. Means what is the cold working process, hot working process, because we are using that terms directly while discussing all these different types of brasses, bronzes, or different types of the alloys. Now, the first in our syllabus is the copper and copper alloys. Okay. Now, before starting the actual copper alloys, first you should understand what are the properties of the copper. What are the properties of the copper? These are copper and copper alloys. Before this, I will explain you, means I will take a little bit a review related to what is the meaning of non-ferrous alloys. Okay, generally metallic materials that we have discussed in the first chapter only, that is metallic materials are classified in two types, that is ferrous materials and non-ferrous materials. Ferrous materials means materials which are having iron as their base element or parent element, and if the material is having other than iron as a base element, other than iron, it may be copper, it may be aluminum, like that, it will be considered as non-ferrous alloys. So copper alloy, okay, means copper will be base element and other element will act as a alloying element. Similarly, aluminum and aluminum alloys will be there. Aluminum alloy, in that case, aluminum will be base element, or you can say that parent element, and other alloying elements will be there. Now, in these copper alloys will be generally classified in two types, that is brasses and bronzes. Okay, copper alloys will be classified in two types, brasses and bronzes, depending on the alloying elements present. Now, what is the meaning of brasses? When in the copper alloys, copper is the base element and zinc is the alloying element. Okay, means alloy of copper and zinc, it will be termed as brass. Alloy of copper and zinc will be termed as brass. And if copper is forming alloy with any other element, okay, with any other element other than zinc, then that will be termed as bronzes. Okay, in this way, copper alloys are classified in two types, brasses and bronzes. When copper forms alloy with zinc, means copper has alloying element as a zinc, then it will be termed as brass. And when alloying element is other than zinc, then it may be nickel, it may be tin, it may be aluminum, it may be you can say that it may be any other alloying element. So depending on that, that bronzes will be there. Means suppose tin is the alloying element in the copper, then it will be termed as tin bronze. If beryllium is the alloying element in the copper, it will be termed as a beryllium bronze. If aluminium is the alloying element in the copper, it will be termed as aluminium bronze. If nickel is the alloying element in the copper, then it will be termed as nickel bronze. In short, when copper forms alloying element with zinc, it will be considered as brass. And if copper forms alloys with any other alloying element other than zinc, then it will be termed as the bronze. And that element's name is given. If suppose tin is there, tin bronze, then beryllium bronze, like this. This is the classification of the copper alloys, that is brasses and bronzes. So now that brasses are have further classified in different types, and bronzes are also having classification depending on their alloying elements, that we are going to discuss in the later half of this lecture. Before that, we will go with the properties of the copper. Now there are some general properties of the copper. you are already aware of this, because you know that copper, already you have studied this copper in the your school. I will repeat it, that is copper, it will be having very good ductility and malleability. Okay, copper will be having very good ductility and malleability, and this ductility and malleability, uh, these properties are there in the copper because of its FCC crystal structure. Okay, face centered cubic crystal structure. Copper has FCC crystal structure. Due to that, generally you have to remember that whenever FCC crystal structure is there, that phase will be soft, malleable and ductile in nature. Due to this FCC crystal structure only, this copper will be having very high ductility and very high malleability. Then the next property is copper. It has high electrical and thermal conductivity, means good conductor of the heat and electricity. You can say that copper is good conductor of heat and electricity. And then these are non-magnetic in nature. Copper is non-magnetic in nature. And another thing related to the copper, copper is having very attractive reddish color. Okay, as when you are comparing the steel and copper, that copper will look very attractive as it is having very pleasant reddish color. Then another property of the copper, you can you can form different alloys, means it can be easily alloyed with the different alloying elements to improve its properties. If suppose you want to improve some specific properties, depending on that you can add different alloying elements in the copper, and it will for you can form different types of the alloys with the help of copper as base element, and different alloying elements you can add like silicon, nickel, iron. Depending on whichever property you want to improve in that, you can add a different alloying elements. And copper also provide you the very fairly good corrosion resistance. As far as general atmospheric conditions are there, it will provide you better good corrosion resistance. But you cannot use this in the very high corrosive environments. Okay, as far as general conditions are there or normal conditions are there, it will provide you good corrosion resistance. So these are the common properties of the copper, and all these properties may be there in their alloys. Some properties will get changed due to addition of the different alloying elements. Now after discussing this copper properties of the copper, uh, we will move towards the next slide. In this I have taken some common applications of the copper and their alloys, and some few, you can say that some specific copper materials are there with addition of some specific alloying elements. Generally you can refer the first point of this slide, that is generally these copper materials are used for manufacturing of the electrical conductors, then different bus bars are there, then automobile radiators, sometimes you can use it for roofing, then you can use it for manufacturing of different kinds of the pressure vessels. Then different types of the utensils are there. Then in the older times you have seen that the coins are also manufactured with the help of only copper material. So different applications are there for this copper and their alloys. Now some two examples I have taken here. Whenever in the copper you are adding 0.3% arsenic element, then that copper will be termed as arsenical copper. And due to addition of this 0.3% arsenic, what will happen? The corrosion resistance of the copper will get increased. Okay, it means addition of 0.3% arsenic will result in improved corrosion resistance of this copper. And due to this, you can use this arsenical copper in the different types of the condenser and heat exchanger to manufacture. Different tubes are there, the tubes are made up of these arsenical copper. Okay, that tubes will be made up of this arsenical copper. Different condensers and heat exchangers are there. Why? Due to addition of this 0.3% arsenic, that copper will provide you better corrosion resistance. That's why you can use it for in the different condenser and heat exchangers. Now if suppose in the copper you have added 0.6% tellurium, then what will happen? Due to addition of this tellurium, the machinability will get improved. It will provide you excellent machinability. Due to this excellent machinability, it will be termed as free cutting copper. Now you can give means you can perform machining operation very easily due to improved machinability. And this free cutting copper is used for manufacturing of different kinds of the bolts, studs, which are made up of copper, then different electrical components like contact pins, switch gears, relays, and other precision electrical equipments you can manufacture with the help of this free cutting copper only. So these are some specific coppers with the addition of some specific elements like arsenic point. When you are adding 0.3% arsenic in the copper, it will be termed as arsenical copper, which will provide you better corrosion resistance, and it can be used for different manufacturing of different parts, which can be used in the condenser and heat exchanger. Generally we are using it for manufacturing of the tubes which we are using in the if you have referred if you have, you can watch that in your refrigerator, that condenser tube is there in your home refrigerator also. You can clearly see that there is one copper tube is there. Okay, that tube is made up of this arsenical copper. In your home refrigerator you can observe it clearly. Then some heat exchangers also, there are some tubes that will be manufactured with the help of this arsenical copper only. And when you are adding 0.6% tellurium, it will be free cutting copper with better machinability, and it can be used for manufacturing of different bolts, studs, and different electrical components. Okay, the last point already I have discussed that, means you can add different alloying elements in the copper to improve its properties. That alloying elements may be zinc, aluminum, tin, phosphorus, beryllium, silicon, nickel, manganese, magnesium, iron, lead, etc. Number of alloying elements you can add depending on the required properties. Okay, so after this discussing the copper, its general properties and general applications we have discussed. After that we will move towards the actual copper alloys. In that already I have told you, I have taken directly here the equilibrium diagram. This we may be asking your exam. This is very important equilibrium diagram, and from this equilibrium diagram only you can easily understand the classification of the brasses. Okay, now you can first you can draw this diagram. Okay, this is equilibrium. This top diagram is the equilibrium diagram, and the bottom diagram, it will show you the mechanical properties. That is on this y-axis. Here on this left side we have plotted the tensile strength, and on this right corner we have plotted the elongation. Two properties are there. And on the x-axis, for both diagrams, here we have taken the percentage of the zinc element. Here it is mentioned that is zinc element, percentage of zinc element from 0 to, and as at this point it is 0. On both diagrams, on x-axis we have taken percentage of the zinc element. At this left corner it is 0, and as you move towards the right hand side, it will goes on increasing. Please draw this diagram. You can write the heading copper and copper alloys. In that copper alloys, you can first write one sentence like the copper alloys are classified depending on their alloying elements as brasses and bronzes. Then you can start write the heading that is brasses and draw this diagram. I will explain it. I will wait for 1 minute here. After completing the diagram, you can mention that in the chat box. I'll wait for 1 minute. 1 or 2 minutes, 2 or 3 minutes is required, I think, to draw this diagram. Please draw this diagram. Whether this diagram is clearly visible. If it is not clearly visible, I will zoom it. Please tell me. Prajwal.
Sir, it is clearly visible.
Okay, okay. Then draw it. Okay. Okay, this is your equilibrium diagram for brasses, and this brasses are nothing but this is a copper alloy. Okay, copper alloys are classified as brasses and bronzes. When alloying element is only zinc with the copper, it will be termed as brasses. And if copper forms alloys with any other element other than the zinc, it will be termed as respective bronze. Suppose copper forms alloy with the tin, then tin bronze. If it forms alloys with the suppose aluminum, it will be aluminum bronze. If it forms the alloys with nickel, it will be nickel bronze. Okay, like this classification will be there. And from that, this is the brasses. This is the general equilibrium diagram for brasses. Now these brasses can further classified in different types depending on their structure, and there is one classification also depending on their color. Okay, after completing this diagram I will explain it. Please draw the diagram carefully. Okay, now we will start with this equilibrium diagram for brass. As the brass is the alloy of copper and zinc. Here copper will act as the base element and zinc will act as the alloying element. Now as far as their melting point is concerned, a melting point of the copper is about 1083 degrees Celsius, and melting point of zinc is about 419 or 420 degrees Celsius. Okay, now in this diagram you can clearly see that on x-axis percentage of the zinc is plotted, and on y-axis temperature is plotted. This is the equilibrium diagram. Now here the equilibrium solubility, okay, equilibrium solubility of copper, sorry, zinc in copper. Here zinc will be added in the copper and they will form a solid solution, means zinc will be completely soluble in the copper. That will be termed as its solubility limit, and it will be having a single phase till that instance. Means whichever amount of zinc is added, it will get completely soluble in the copper, and it shows you only one phase, and that phase will be alpha. It is solid solution of uh, copper and zinc. Okay, means completely soluble in each other. And up to 38% zinc, there will be only one phase, and that phase is the alpha, up to 38% of the zinc. And when zinc amount goes above that solubility limit, above that solubility limit, that is more than 38% zinc is there, then a new phase will appear there, and that new phase is beta phase. Beta phase will be there, beta phase will be there. And This beta phase will exist in two form. Okay, this is the beta phase. This beta phase exists in two form, as indicated in this equilibrium diagram by beta and beta dash. Beta and beta dash. You can say that these two forms are, you can say that, depending on their nature of the formation of the solid solution, this beta dash will be ordered solid solution. Okay, this will be ordered solid solution, and this beta will be disordered solid solution. Okay, you're getting this beta and beta dash above this 453 degrees celsius or 470 degrees celsius, there will be phase beta, and below this beta dash will be there. Means this beta phase will exist in two forms, that is beta and beta dash, depending on the temperature. At lesser temperatures, that is below this 453 degrees celsius, this beta will exist as only beta, and you can say that it will be a ordered substitutional solid solution. This beta dash, here dash is not written. Okay, here beta dash is here, beta dash, beta dash. Below 453 degrees celsius, beta dash will be there, that is ordered phase. Okay, that is ordered phase. Hello, this. Okay, beta and beta dash is there. I will repeat it again. Up to whenever zinc percentage is up to 38%, only one phase is there, that is the alpha phase. When zinc percentage goes above 38%, a new phase will appear. That phase will be beta phase, and this beta phase exists in two form, that is ordered beta phase and disordered beta phase. Now, depending on this temperature only, below this 453 degrees celsius temperature, that beta will be ordered form. In the that solid solution will be in the ordered form that we have discussed in the first chapter only, types of the solid solution. In that, substitutional solid solution has two types, ordered and disordered. That same types will be here. This beta will be disordered substitutional solid solution, and beta dash will be ordered substitutional solid solution. And below this 453 degrees celsius, it will be ordered, and above that it will be disordered. Okay, and when this percentage of zinc is up to 44%, up to this, means below 38% only one phase is there, alpha phase, and above 38 to 44% two phases will be there, that is alpha and beta. Alpha will be there and beta will be there. And when zinc percentage is more than 44%, then there will be only one phase, that is only beta phase, and the beta will appear in two forms depending on the temperature. Either it will be ordered or it will be disordered. And when the percentage of zinc goes above 50%, again a new phase will be there, and that new phase will be termed as gamma phase. Gamma phase. Okay, gamma phase will be there. And this gamma phase is very brittle in nature. Generally, whichever commercial brasses we are using, that brasses are either alpha brasses or alpha beta brasses. We are not using this above this, means after this 453 degrees celsius, there will be brittleness in that all alloys. That's why all we are not using these in your our practical life. Okay, up to this, means up to 44% only we are using in the practical life, these all types of the brasses. Either it will be alpha brass or it will be alpha beta brass. Now, microstructure, depending on the basis of their structure only, these brasses can be classified as alpha brasses. Okay, alpha brasses, alpha brasses and alpha beta brasses. Whenever percentage of the zinc is less than, you can say that 38%, it will be termed as alpha brasses. And when percentage of zinc is in between this 38 to 44%, it will be termed as alpha beta brasses. As in their microstructure you will be able to see two phases, that's why it will be termed as alpha beta brasses. Then above this 44% beta brasses, and above 50% beta dash gamma brasses are there. But this beta and beta dash gamma brasses are not used in your practical life. So only two types will be, we are going to consider only two types, that is alpha brasses and alpha beta brasses. Okay, so this is the your equilibrium diagram, and this will be your explanation, that is you have to explain related to their classification as alpha and alpha beta brasses, and how they are classified depending on the amount of the zinc. And you have to explain that up to 38%, the equilibrium solubility limit is 38% of zinc, and up to that 38% of zinc only one phase is there, that is alpha. And when amount of zinc goes above 38%, a new phase beta will appear there, and this beta will exist in two forms. One form is ordered and another form is disordered depending on the temperature. Above 453 degrees Celsius, beta is in disordered form, and below 453 degrees Celsius, beta is in ordered form. And when percentage of zinc increases above 44%, then there will be only again a single phase, that is beta phase only. And when percentage of zinc goes above 50%, and then again a new phase will exist there, that is the gamma phase. And this gamma phase is very brittle in nature, that's why we are not going to use it in the practical life. Up to only this, that is some brasses are there max 50% zinc, above that we are not using it in the practical life. What will be the then what will be the effect on the properties of that, means what will be their tensile strength, then what will be their changes on their ductility. You can say that depending on the percentage of zinc only, these properties will also vary. Now that explanation you will get from this second diagram. Second diagram is there. Okay, mechanical properties of the brasses. Again, on x-axis, percentage of zinc will be there, and on y-axis, toward this left corner, we have taken tensile strength. On this right corner, we have taken the elongation. Okay. Now here, as percentage of zinc goes on increasing, as percentage of zinc goes on increasing, up to 30% zinc, ductility, tensile strength, both increases. And when the zinc amount goes above this 30%, ductility of that material starts decreasing. This is the elongation. You can get it, ductility of that material means when zinc amount is increasing up to 30%, ductility of that material also increases. And when zinc amount is more than 30%, then ductility of that material starts decreasing. Means whenever there is alpha phase, it will be having very good ductility also, and tensile strength will be also comparable, or you can use it in all practical applications. Then what about the tensile strength? Now tensile strength goes on increases as amount of zinc increases, and it is maximum when the percentage of the zinc is about 44% here, about 44 or 45% maximum tensile strength will be there. And above that, when this only beta dash phase is there, then after that we will start that tensile strength also drops. And when gamma phase appears, it drops suddenly. Okay, means up to alpha beta, it will provide you better strength, tensile strength. Now from this diagram it is clear that this alpha phase is soft and ductile in nature with a very good tensile strength. And this alpha beta, it will be having lesser ductility, but tensile strength will be very high. And above that 44%, it will not be having any tensile strength, or will not be provide you the required ductility or toughness. Means it will become brittle in nature. It will become brittle in nature. So this is the explanation related to the equilibrium diagram and their mechanical properties, depending on the amount of zinc and phases existing in that type of brass. Okay, so this is the explanation for the equilibrium diagram. If you're having any question in this, you can ask me. Otherwise, we will move towards the next point. Ah, yes.
Hello, sir. Sir, that 9.
What? Hello? Hello?
Yes, sir.
Ah, yes. You can ask.
Sir, that J point, that part I don't understand.
Which point? Which?
J point, 905 degree centigrade temperature part.
J point. This point you are getting.
Yes, sir. Liquid.
Above this, it will be, that for this particular composition, if you take vertical line from this, suppose it will come in this range 40 to 50%. At this particular composition, above this 905 degrees Celsius, that alloy will be in liquid state. This is only diagram, means this above line, whichever this top line is there, means I will explain it. At this point, if you look at this top point F, okay, this is melting point of the copper. Above one, approximately melting point is 1083 degrees Celsius. And as you are adding zinc, okay, as you are adding zinc, its melting point goes on decreasing. It will decrease. And at about 44% zinc, it will become 905. Okay, this 905 means, as we are adding the zinc in the copper, and when it becomes approximately 44%, means copper plus zinc alloy will be there, and this zinc will be 44%, and that alloy will be having melting point 905. And in the same way, when zinc amount is more than 60%, its melting point will be 835 degrees Celsius. It is just indicating the melting point. This J point, it will indicate the melting point. Above that, it will be in the liquid state, that particular alloy. If you go through this top line, it will indicate that as zinc percentage is increasing, melting point of that alloy will drop slowly. And at this particular composition, this will be 44% zinc. At that point, melting point of that particular alloy will be 905. And at this particular point, when zinc is 60%, its melting point will be 835 degrees Celsius. Okay, is it clear?
Yes, sir. Sir,
Yes.
and that below 32 J line, that what represents, sir?
Below 32 means which line you are getting?
32 G, that point.
32 means this 32 is nothing but the percentage of zinc here. This is 32% zinc. This horizontal line will start from 32% zinc. It will come here, somewhat here at this point. 32% zinc means in this loop here, alpha and liquid phase will be there. Okay, and this horizontal portion where it will get transformed to alpha and beta, this temperature will be 905. Okay, from this point you will get 905. And this is the 32% zinc. This 32 is the composition of that particular alloy. 32% zinc. This degree Celsius will be 905 degrees Celsius. That will be the melting point for that particular alloy. And this is the composition of that alloy. At this point G will start from 32% zinc. If you take the vertical line from here, you will get end up with 32% zinc. It is indicating that only. Okay, are you clear with this?
Yes, sir. Yes, sir.
This is nothing but the composition. This is the composition only, means percentage of the zinc, and this is the temperature only, that is melting point for this particular composition. Okay, can I move towards next point?
Yes, sir. Yes, sir.
Okay, okay. Okay, I will explain this first. Now, the brasses are classified depending on the there is microstructures also, and one more classification is there for the brasses depending on their color. Okay, depending on their color, and this color will also you can judge that color by understanding the percentage of the zinc. Okay, whenever percentage of zinc is less than 20%, whenever percentage of zinc is less than 20%, then that brasses are termed as red brasses. Okay, red brasses and yellow brasses. Here I have taken some pictures of their components. Here these are the components manufactured from the red brasses. You will find that they are having reddish color. Okay, somewhat reddish color, means here in this case percentage of copper is very high. In the red brasses, percentage of zinc will be less than 20%. Whenever percentage of zinc is less than 20%, it will be having reddish color, and that brass will be termed as red brass. And whenever brasses has zinc more than 20%, then it will be having yellowish color. That's why it will be termed as yellow brass. Okay, so this is the classification depending on their color, and that color will be decided by the percentage of the zinc only. When zinc is in the lesser amount, that is below 20%, it will be having reddish color, and it will be known as a red brass. And when zinc will be in higher amount, that is more than 20%, then its color will become yellow. That will be termed as yellow brass. And yellow brasses are generally having lesser cost. Yellow brasses are having lesser cost because in copper and zinc, zinc will be cheaper, or with the it will be available with the less cost. And as zinc increases, its cost will goes on decreasing. In that sense, you will get that yellow brasses will be having less cost, and this red brasses, as copper is costlier than the zinc, this copper red brass will having more cost. Okay, reddish color means less zinc, lesser than 20% zinc and more copper, and as copper is more, its cost will be more. And yellow brass, here zinc will be more than 20%, and copper will be lesser. Due to that, you will find that it will be having yellow color, and it will be termed as yellow brass, and its cost will be less, as you can purchase the zinc with the lesser price. Okay, this is the classification, that is red brass and yellow brass depending on their color. Okay, and now the brasses can be classified depending on their structure. As here we have seen that that is the alpha brass and alpha beta brass. Whenever the zinc percentage is less, as here we have seen that at particular this point 30%, before this it is having ductility also and tensile strength also. That's why they have taken for practical purpose exactly at this point 30%. Alpha phase exists up to 38, but for practical purpose, as it will provide you ductility and toughness along with the tensile strength, they have made the classification in such a way that 30% up to 30% zinc and remaining copper, it will be termed as alpha brasses. And whenever zinc is 30 to 44%, okay, less than 30% zinc, it will be alpha brasses. and when zinc is in between 30 to 44, actually it is 44. In some books, if you refer that code gire or that Avner book, you will find that this amount sometimes it will be 30 to 40, or in some books they have given 30 to 44% also. It will be fine. That is, in general, you can say that whenever zinc is less than 30%, it will be alpha brass, and whenever zinc is in between 30 to 44%, it will be alpha beta brass. Now, as zinc amount is less, zinc is less and copper is more, it will be expensive. It will be expensive. And as here zinc amount is more, it will be cheaper. We are just comparing these two. As compared to alpha brass, alpha beta brasses will be cheap. Now, related to the properties, these three different points will be related to their properties. As zinc percentage is less and copper is more, it will be soft, malleable, and ductile in nature. And here, alpha beta brass, it will be hard and strong in nature due to presence of this beta phase. And why this is soft and ductile? Due to presence of this alpha phase, it is soft, ductile in nature, and it will be hard and strong due to this beta phase. Then it will provide you good corrosion resistance, and it will be having better corrosion resistance as compared to alpha beta brasses. Okay, alpha beta brasses will also shows the corrosion resistance, but as compared to alpha brasses, its corrosion resistance will be poor. Now, as it is soft, malleable, and ductile, you can do the cold working operation on this alpha brasses. And as this alpha beta brasses are hard and strong in nature, you have to do the hot working operation to give the exact shape and size to that particular material. For example, alpha brasses, these are some practical examples of that alpha brasses. That is cap copper, then gliding metals, sorry, gliding metals, then cartridge brass, admiralty brass. These are examples of alpha brasses. For alpha beta brasses, Muntz metal, naval brass, leaded brass, high tensile brass, and brazing brass. And these are the examples of the alpha beta brasses. Okay, whichever examples I have written here, these four types and these five types, all these four, means totally nine types we are going to discuss in the next lecture, along with their composition properties and their specific applications. In your examination, they will ask you, or they will provide you directly three names, three or four names. Like they will provide you cap copper or cartridge brass, or they will provide you high tensile brass or leaded brass, and they will ask you to write their composition properties and applications, and they will provide you any three names from this list. Compulsory, this question will be there in your final examination. And all these types of alpha brasses and alpha beta brasses we are going to discuss in the next lecture. Okay, so I will stop here. In this lecture we have discussed about the properties, how the metallic materials are classified in ferrous and non-ferrous alloys. And in non-ferrous alloys, we have started the copper and copper alloys. We have discussed about the properties of the copper, then some general applications of the copper, and some few general types with addition of their alloying elements. And then we have seen its classification in the brasses and in the bronzes. Then specifically brasses we have started. We have seen the classification of the brasses depending on their color and depending on their phases or microstructures. And we have discussed the equilibrium diagram for general brass materials also. Now in next lecture we will discuss about their specific applications, means specific applications in the composition properties and application of these four types of alpha brasses and these five types of alpha beta brasses that we will discuss in the next lecture. Okay. Okay, if you are having any query, you can ask that query. Otherwise, I will stop here. I'll stop the recording. Thank you. Mm, if you are